Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're continuing our examination of organic chemistry by looking at amines. Amines are organic compounds that contain trivalent nitrogen. The nitrogen is sp cubed and usually has a lone pair of electrons, as you see here. The three R groups can be alkyl, aryl, or other groups, such as some hydrogens. Now, with regards to classification, there's some special changes necessary for amine chemistry. In order to understand these changes, it's best that we look at how alcohols and alkyl halides and other compounds are classified. I've drawn a series of organohalides here, and we're going to take the time to classify them. Now, classification is determined if you have a monovalent group like bromine by looking at the carbon that the bromine's attached to and finding out how many carbons are attached to that carbon. In the case of methyl, which has no carbons attached to it, it's referred to as a methyl group, and so this is a methyl halide. We often just give it the symbol Me. Refer to it as methyl. The next halide, off of the carbon, there is one carbon attached to it, so it's referred to as a primary or first degree halide. The carbon bearing the bromine has two carbons in the next molecule and referred to as a secondary alkyl halide. And lastly, the carbon bearing the bromine has three carbons to it. It's a tertiary halide. Now, this system works for any monovalent group. For example, if I replace bromine with alcohol groups, the same designation applies. So the first methanol is classified as a methyl alcohol. Ethanol is referred to or classified as a primary alcohol because the carbon that bears the OH has only one carbon attached to it. The OH group in isopropyl alcohol is attached to a carbon that has two carbons off of it, so it's secondary. And the OH group in tert-butyl alcohol is attached to a carbon that has three carbons off of it, so it is tertiary. So there you have it, methyl, primary, secondary, and tertiary. Now, what happens if I apply or make analogous compounds that bear the amine functional group? So here is a methylamine. Ethylamine. Isopropylamine. And of course, tert-butylamine. So essentially, I've generated the analogous amines to the alcohols that we've talked about. Well, classifying amines is a bit different than classifying alcohols. You see, amines need not only be monovalent. The hydrogens can be replaced with alkyl groups. If you replace the H on oxygen, you change the functional group. You're no longer an alcohol. If this H is turned into a carbon, you now have an ether. But if the H is on an amine, any of these amines is replaced with carbon, you still have an amine. So in terms of designating or identifying the functionality of the amine, instead of looking at the carbon that the nitrogen's attached to, you focus on the nitrogen. And you look at the number of carbons directly attached to nitrogen. If nitrogen has only one carbon attached to it, it is primary. If nitrogen has 2 carbons off of it, it's secondary. If nitrogen has 3 carbons off of it, it's tertiary. And if nitrogen has 4 carbons off of it, it's quaternary. Now, if I was to classify these amines using that methodology, this nitrogen has 1 carbon. This nitrogen has 1 carbon attached to it. This nitrogen has only 1 carbon directly attached to it. This nitrogen only has 1 carbon directly attached to it. They'd all be primary. Now, in fact, the methylamine is often referred to, okay, even though it is primary, as methyl, a methylamine. And that's consistent. But you notice the difference. All of these amines are designated primary, where in the alcohol case they were all different. Right. So you need to be aware of this different methodology of classification. If that is the case, what kind of amines structures could I make that would actually give me different classifications? Well, again, I said it's focusing on the nitrogen. So what we're going to do is we're going to start with a primary. As pointed out, ethylamine, CH3, CH2, NH2 is primary. What would be an example of a secondary? Well, I could have 2 ethyl groups bound to a nitrogen. In this case, that would be secondary. And if I had 3 ethyl groups, that would be tertiary. And nitrogen that has 4 carbons off of it is a cationic salt. Possesses a positive charge. And so you actually can have quaternary or 4-degree nitrogen-containing species. Now, it's not truly an amine because the lone pair is gone. It's more an ammonium cation, whereas all the other nitrogens had lone pairs. There's no lone pair here, and that would be a 4-degree nitrogen-containing salt. Okay. So the classification methodologies for amines is somewhat different from that of other functional groups that we have covered, specifically the monovalent species, such as alcohols or alkyl halides. Let's move on now and take a look at nomenclature. And let's examine, we'll begin with IUPAC. nomenclature for amines. Now amines are named as alkanes in which the E ending of ane is dropped and replaced with amine. Substituents attached to nitrogen are identified by the locant N. For example, if I have the following molecule, what we have here is propan, one amine. In this case, the one is necessary because you could have the propane, the amine off of carbon 2 of the propane. What happens if you have two alkyl groups off of the nitrogen? Well, when they're identical alkyl groups, you look for the longest carbon chain, standard rule of IUPAC, but if they're identical, you just pick either one. And one becomes a substituent off nitrogen, and one is the parent root. So this is an ethane. Drop the E, it's an ethanamine. I could say ethan-1-amine, but no matter where I put the N, it's ethan-1-amine. So this is an ethanamine. And we have an ethyl group off nitrogen. So this is N-ethyl. N-ethyl ethanamine. When it is asymmetric, you find the longest carbon chain with the nitrogen off of it. So if I have something like this, the longest carbon chain with the nitrogen is 1, 2, 3 carbons. This is a propane, and at carbon 2 we have an amine. So this is propan, two amine. And off of the nitrogen, we have a methyl, so we have N-methyl propanamine. If we have a ring, and off of the ring we have an amine, again it's named simply as an alkane. We have a cyclohexane. We drop the E, we got cyclohexanamine. I could say 1, but no matter where the NH2 appears, that's where you start counting on the ring, so it has to be 1. So this is simply cyclohexanamine. Cyclohexanamine. Notice if you have several substituents off of the nitrogen, several substituents. Again, the longest carbon chain, 1, 2, 3, 4. 4 is a butane. Drop the E, it's a butanamine. In butanamines, you could have butan-1-amine or butan-2. This is off of carbon 2. So this is butan-2-amine. And then we have two methyls off of nitrogen, so we say, just like we would in numbers, one N for each methyl, NN dimethyl. NN dimethyl butan 2-amine. Now, there are cases where common nomenclature has been adopted by IUPAC. Specialized names can be used often opposed to systematic method that we've just covered. Two examples are the case for benzenamine and for methyl benzenamine. So let's look at these two examples. If I was to follow the previous systematic method, I would name this molecule as benzene. If I drop the E, I would add amine and it would be called benzenamine. But this molecule had a common name that is so commonly used that it's adopted by IUPAC. Instead of saying benzenamine, we'd say aniline. The molecule is given a special name. And some molecules common names even overrule the use of aniline. For example, if I was to use aniline to name this molecule, I would count from the nitrogen, because as soon as you use the word aniline, you've got to make this number 1. 1, 2, 3, 4. That would be 4-methyl-aniline. Well, 4-methyl-aniline, although it's acceptable, is not the usual name. Often we say 1,4-toluidine or 4-toluidine or para-toluidine. It's a toluene combined with an aniline, and so it's given the special name toluidine. Okay? Or often you would say 1,4-toluidine. Or just 4. All designations have been used. Now, if you have a higher priority functional group on the chain than amine, then the amine is brought out front as a prefix referred to amino. So if you have, for example, NH2, CH2, 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 OH. Alcohols are higher priority in nomenclature, and as a result, the root name would be propan-1-ol, propanol. And so the NH2 comes out front as an amino, and you'd count from the highest priority group, 1, 2, 3. This is a 3-amino, propan-1-ol. Some cases the amine is lower priority and it's rather complicated. It's not an NH2, it might have a CH3 off of it. If I have a carboxylic acid functional group, the carboxylic acid is clearly higher priority. And so this is 1, 2, 3, it's a propanoic acid. So we have propanoic acid. Now, when there is no simple name for the substituent, IUPAC methodologies are used. This is an amino group, but off of the amino group we have a methyl attached to a nitrogen. So this is an N-methyl amino. When you use this methodology, you were taught that you had to place the name in brackets. N-methyl amino is placed in brackets, and then the locand of where it's attached to the main chain, 1, 2, is put up front. So this is a 2N-methyl amino. And of course, if there's more than one specialized name, you pick the specialized name as the root that has the highest priority group in it. For example, in this case, if I use the NH2 in the root, the specialized name is aniline. If I use the OH in the root, the specialized name is phenol. Since OH is higher priority, it is better to call this molecule a phenol. And bring the NH2 out front. It's attached to carbon 4 as 4-amino phenol. 4-amino phenol. Okay? Not 4-hydroxyaniline. Now, amines can find themselves actually in the ring structure. We can draw a series of amines where the nitrogen is actually inside the ring itself. For example, we could have a nitrogen in a 5-membered ring. Now, when you have nitrogen in a ring like this, these are referred to as heterocyclic rings. They're called heterocyclic when one or more atoms in the ring are not carbon. We could have it in a 6-membered ring. We could have a 6-membered ring that has 2 nitrogens. Or we could have a heterocyclic 6-membered ring where one atom is oxygen and one atom's a nitrogen. All of these have amines in the rings, and they all have specialized names. The first one is called pyrrolidine. The second is referred to as pipyridine. The third is pipyrazine. And the last structure is referred to as morpholine. Now, if we want to learn how to number substituents off of these rings, we have to think right back to the numbering system used in epoxide chemistry of last semester. In epoxide chemistry, which was also a heterocyclic ring, we learned that when numbering the ring, oxygen always got number 1. And so you either had a 2-3 or a 2-3. But oxygen was numbered 1. This is a common methodology in numbering heterocyclic rings. In fact, it is pretty much the case here. The nitrogen of the ring causes a fixed numbering system. The nitrogen always gets 1. You go to the lowest possible numbering system. Now in pipyrazine, you could give either nitrogen number 1. But in morpholine, because oxygen's higher priority, the oxygen always gets number 1. So if I had a substituent in morpholine, that appeared near the nitrogen, I can't go 2 and number the nitrogen ones. This morpholine's number 1. That's 1, 2, 3. The best I can do is say 3-methyl morpholine. Methylmorpholine. All right. If I have a substituent of pyrrolidine, say a methyl here, okay, well that's obviously 2, because the N gets number 1, 2-methyl pyrrolidine. So some new names for you to memorize in IUPAC nomenclature. Now, the terminology pyrrolidine, piperidine, piperazine, morpholine, these names often occurred prior to IUPAC nomenclature, and some of them are common names. Which brings us to the common nomenclature utilized for the naming of amines. Under common nomenclature, amines are named as alkyl amines, all one word, and again, N is used as the locant to identify substituents. If we go back to some of the amines we drew first, such as propanamine, 1-propanamine, or propan-1-amine. 1-propanamine, you'll notice, has a propyl group off the nitrogen. And so in common nomenclature, all one word, it is named as propylamine. Propylamine. In the case where we had 2 ethyl groups, and we had N-ethyl ethanamine, well, in this case, we have 2 ethyls attached to a nitrogen. So in common nomenclature, instead of saying N-ethyl ethanamine or N-ethyl ethylamine, we just say di. When there's 2 identical groups, you just say dialkyl, diethylamine. If there were 3 identical ethyl groups off, we'd say triethylamine. Okay, diethylamine. In the case where there were different groups, well, the longest chain again gets the root, and we use N as a locant for the other. So in this case, we have N-methyl and a root, the nitrogen attached to this propyl. It's an isopropyl group off of it, so it's isopropylamine. So N-ethyl isopropylamine. And again, in common nomenclature, the heterocyclic names are the same: pyrrolidine, piperidine, piperazine, and morpholine. In many cases, the common name is used far more than the IUPAC name. In some of those cases, IUPAC has adopted the common nomenclature. Now, such as in the case of aniline. Another piece of nomenclature that's very important that we must look at is the nomenclature of the quaternary nitrogen, the nitrogen that's positively charged. I refer to this as amine salt nomenclature, but it is based on the chemistry of NH3 when it's picked up a proton. In its simplest case, although we don't consider water an alcohol, and we don't consider ammonia an amine, NH4 plus Cl minus is probably the simplest example. And it's two words. It's named as an ammonium salt. Ammonium chloride. So, ammonium chloride. Now, when you protonate an amine, amines with special names have the E ending of the amine replaced with IUM. For example, the specialized name aniline when aniline's lone pair picks up a proton and it becomes an NH3 plus, aniline becomes anilinium ion. Whatever I draw as the counterion is named as a separate word. So again, if I have Cl minus here, I have anilinium chloride. Two words. If an alkane amine becomes cationic, it is named as an aminium ion. However, if the cation is the result of a quaternary nitrogen with 4 alkyl groups, it's often referred to as an alkyl ammonium. Let's take a look at this, if we could. Let's draw two examples that bear this out. Suppose I started with this amine. I have an isopropyl and I have two methyls off this amine. And I react this amine with acid, so it protonates and it picks up an H. And that makes a positive ammonium salt. Now suppose I take the same starting amine, but this time I attack a methyl iodide. So it can do nucleophilic substitution. Now it is tertiary, the reaction may be very slow. This amine is tertiary, it's quite bulky, but with a methyl it might go. Let's assume it does go. So nucleophilically attacked methyl iodide and put a methyl group here. Now when there is a quaternary ammonium salt, not quaternary in this case, it's a tertiary ammonium salt, that still has an H on it. It's named as an amine, and we drop the E and add IUM, so it's aminium. Now if I was to name the amine without the H, I would have NN dimethyl propan-2-amine. So I'd have N dimethyl propan-2-amine. Okay. Now when it's positively charged, the E is dropped and I had IUM. And if I had a Br minus here as the counterion, I'd have an N-dimethyl propan-2-aminium bromide. The common name, of course, is named as an isopropylamine. And so I'd have NN dimethyl and what's interesting to note is sometimes the NN's not used. They just say dimethyl isopropylamine. But NN dimethyl isopropylamine. But again, drop the E, add IUM. Bromide. Okay. So that is this molecule. How do we name the one that has 4 carbons, the quaternary ammonium salt? Well, it is typically named as an ammonium salt. And we would call it trimethyl isopropyl. Instead of aminium, it gets called ammonium. And if there was a Cl minus, let's say, as cation, this would be a chloride. It would be perfectly fine to say N, N, N. So put in your N's if you can. NNN trimethyl isopropyl ammonium chloride. So there is a difference in designating a cationic nitrogen that has a hydrogen versus a cationic nitrogen which has only carbons. In the case if there's only carbons attached to it, it's referred to as an ammonium salt. If there's an H off of it, it's named as an aminium salt. Okay. Well, let's take a look now at the physical properties of amines. Physical properties. Now, we know nitrogen is quite electronegative, and it can produce a dipole. But nitrogen typically is less electronegative than oxygen. So, although nitrogen bound to a hydrogen can produce hydrogen bonding, the dipole that results is weaker than in the case when there's an OH. So if we look at 3 molecules that have 4 carbons, 1 diethyl ether has no hydrogen bonding, 1 diethylamine has hydrogen bonding, and the other 1 butanol has hydrogen bonding. And we compare the boiling points. 34.5 degrees C for diethyl ether, 56 degrees C for diethylamine, but 117 degrees C for butanol. The reason for this increasing trend in boiling point as we go down is as follows. Diethyl ether lacks hydrogen bonding and so has the lowest boiling point. Nitrogen's electronegative, produces a fairly large dipole, but the dipole is smaller than that produced in the case of oxygen. Oxygen is more electronegative, withdraws electrons more, bigger dipole, so the intermolecular force is stronger because there's larger separation of charge. The hydrogen bonding interaction is weaker in an amine than in an alcohol. You should note that tertiary amines, like ethers, lack hydrogen bonding. So if I look at a molecule like trimethylamine, trimethylamine has no H off the nitrogen, so its boiling point is only 3 degrees. If we compare that to a 3-carbon amine, such as 1-propanamine or N-propylamine, which has hydrogen bonding but also has 3 carbons in it, its boiling point is 48 degrees C. And although they have the same number of atoms, same number of carbons, one could ask, well, why the difference? It is clearly due to hydrogen bonding in this case. Now, because of hydrogen bonding and the availability of lone pair, low molecular weight amines are very water soluble. But as the carbon chains grow, solubility decreases. Another property of amines is their very powerful odor. Amines have very strong odors and often find themselves in use as smelling salts. The odors are so powerful they can often cause a person to rouse from unconsciousness. Many amines are toxic, especially aeroamines. Amines such as aniline, or beta-naphthylamine. This guy is 2-naphthalene amine. It's its IUPAC name. Common name is beta-naphthylamine or naphthylamine. Many of these are toxic and very readily absorbed through the skin. And molecules like beta-naphthylamine are carcinogenic. Quaternary cationic salts and ammonium salts, or aminium salts. So quaternary ammonium salts or other aminium salts, because of the ionic nature, are very polar molecules, often water soluble. And they possess properties more typical of inorganic salts: high melting points and water solubility. Now we have to go way back to first semester if we want to understand some of the structural features of an amine. Amines have trivalent nitrogen atoms. They have a lone pair of electrons, and counting the lone pair, they can be chiral. I can put 3 different groups around my nitrogen. Now, nitrogen's sp cubed, and with the 3 different groups and the lone pair, the molecule would be chiral. But at room temperature, there's enough energy for the molecule to rehybridize to sp squared. Where the lone pair is in a pure 2p orbital. Because this is higher energy, it is short-lived and it can go back. But the 3 groups now can flip up and if it does, you get this structure where the lone pair of electrons are in an sp cubed orbital down. Now what's interesting is this flipping process, inverting the 3 groups, produces the opposite enantiomer. If I was to name the molecule, and I'll just use the common name here, this is S-N-ethyl N-methyl propylamine. And once the groups have flipped up, it has now become R, N-ethyl N-methyl propylamine. All one word. Because this racemization of a chiral amine occurs at room temperature, amines are not typically resolvable at room temperature. They undergo inversion of the chiral center. It's often called inversion, and in fact was one of the first mechanisms, even though it's not a reaction, first mechanistic explanations that you received when we were studying chirality last semester. Temperatures would have to be greatly reduced to prevent such an inversion process. When inversion is prohibited, you can isolate a pair of enantiomers. 2 examples of molecules where such inversion can be prohibited are Troger's base So there's a carbon there and a carbon here. This molecule is often referred to as Troger's base. lone pairs off of the nitrogen, because it's pinned back and is tied in this bicyclic ring structure, it's prevented from inverting. And as such, it is chiral and doesn't invert. Another is this molecule. Let's make a little more room. So we have a nitrogen here. This is 1-aza. Aza indicates the nitrogen. Bicyclo. It's bicyclic. 2,2,2. And octane. Bicyclo 2,2,2-octane and 1-aza. Again, it's pinned back. There's a lone pair off the nitrogen. Because it's tied back, this molecule can be stopped from undergoing inversion. If we put substituents on it that would make the groups different, then it could be chiral. And if it was made chiral, it could be resolved into pure enantiomers. Last point to note is that ammonium salts with 4 different groups can be chiral. So this has 3 CH2, so that's a butyl group. Here's a propyl. Four different groups around an ammonium salt can produce a chiral ammonium salt. This molecule's chiral. If I was to name it, I could have R butyl ethyl methyl propyl ammonium chloride. Ammonium chloride. Naming all the alkyls as substituents, often an ammonium salt. There you go. Okay. So that's it for physical properties. Next Scribblecast lecture, we'll take a look at the preparation of amines and start looking at some of the reactions that can actually yield amine as product. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.